Thanks, Lenore, for the fantastic introduction. It's a great pleasure for me to be here. I'm going to talk about deductive verification of probabilistic programs, subtitle From Theory to Automation. So the true story is that I was reading the book of McIver and Morgan on a great book on probabilistic programs. That was around 2009. And I couldn't really grasp it, so what I decided to do is just go down under, visit them, try to work with them together. Then we collaborated by co-supervising a PhD student. And then slowly I got into this, and it took me quite a bit before I really understood, and I'm not pretending that I really understood now, but before I got, let's say, I got a kind of good grasp of what are probabilistic programs. Since then, I had several brilliant PhD students. I acquired an ERC grant on, let's say, deductive verification of probabilistic programs. And it's a great pleasure for me to basically present here. And I'm only the messenger because the basic work has been done by those brilliant PhD students. So here's my roadmap. I will first get to the motivation. And then I'm going to set the scene by going back to good old Dijkstra's weakest preconditions. That's going to be happening in 2, so no probabilities. Then I'm going to talk about weakest preconditions for probabilistic programs. That's section 3. Then I'm going to show you that you can actually extend this by reasoning about the runtime and actually the expected runtime of a probabilistic program. So there the question is, how long does a probabilistic program run on average? Then we're going to talk about loop invariants. Like ordinary programs, loop invariants are basically the hard part in probabilistic programs. And then we are going to deal with some kind of relative completeness result. I'm going to briefly touch upon a syntax to express weakest expectation or weakest expectations. And then I will give you 4 types of different, I would say, prototypical kind of tools to give you a kind of intuition and flavor on what's the state of the art in automating this kind of thing. So let's start with the motivation. We're going to talk about probabilistic programs. In my talk, there will be sequential programs. And we're going to talk about programs where you have random assignments. This means you sample from a distribution, and then you assign the value to a variable. And we have conditioning, and I'm going to explain that later on what that means. But intuitively, this means that you can basically observe certain frames from data, and then you can condition a distribution based on that data. And actually, I must admit that this conditioning actually is one of the reasons why probabilistic programming is actually nowadays quite getting more and more, let's say, attention. So you can code up randomized algorithms, and I will give you some examples. Probabilistic programs can represent probabilistic graphical models that go beyond the expressive power of Bayesian networks and Markov fields and so on. You can use them to model, let's say, controllers that have to do stochastic decision making, that happen, for instance, in robots, that have to go from a source to a target. They're also used to describe security mechanisms. So several groups working on probabilistic programs to describe security mechanisms, try to do verification of those mechanisms, and so forth. And this is the bunch of programming languages. So R2 is a language developed by Microsoft. There is a language Stan, which is actually used in the financial to do financial predictions for auction markets, for instance. Pyro is a variant of Python. This has been developed by Uber. So it's the same company where you order your cabs from and so on. PyMC, also an extension of Python. Web People, developed in Stanford by Noah Goodman and his group, and they are cognitive scientists. And this is based on JavaScript. And then there is this language developed by Microsoft, actually by Andrew Gordon and his group. That's actually a probabilistic extension of Excel. And now you may ask, is Excel a programming language? Well, according to Andy Gordon, it's the most used programming language on the globe. So I'm pretty sure it's a programming language. And I like this quote that I took from this paper in 2014. Probabilistic programming aims to make probabilistic modeling and machine learning accessible to the programmer. Good. I must admit that probabilistic programs in reality, so out there in machine learning, they're typically using lots of continuous distributions. In my tutorial, I'm going to stick to discrete probability distributions. And I hope to convince you that this is already interesting enough, B, difficult enough, and therefore let's first try to understand this before we go to continuous distributions. Now people ask me always, can you give me some applications of probabilistic programs? I give you 3, and I think they're really exciting about these programs. So this is a program, it's a probabilistic program developed by Stuart Russell at Berkeley and his group. It's called NetVisa. It's the system used by the United Nations to actually analyze seismographic data. So you want to know, is there an earthquake? Where did it happen? How deep in the earth did it happen? Or was it perhaps a nuclear bomb test or something like this? And there is a whole system of stations around the world. They gather all this data goes to Vienna, and they use a probabilistic program that's trying to actually predict where this seismographic event occurred and what was the cause of it. I also like this. This is developed by Sesha and his group, and they use a probabilistic programming language called Scenic. It describes scenes, so scenes like cars on streets and so on. And what they do is they use those programs to generate test data to train neural networks. Okay? Because in those neural networks, I mean, training is a specific difficult issue normally. And what they do here is that they just give one program, and think about this program as a kind of symbolic representation of many different scenes. It's basically a kind of generator that generates scenes, and those scenes are individual tests or individual training data for your neural network. And they showed some very interesting comparisons to standard, let's say, training of neural networks. And they did this for some computer vision applications. This was published, I think, last year in the Machine Learning Journal. And then I'd like to mention this application over here. This is a publication in Science a few years ago by Tenenbaum and his co-authors. And this is by about basically handwritten, you have handwritten symbols, like in a language, Arabic, Hebrew, or something like this, and now you would like to recognize this. And what they did is they compared the capabilities of humans against the capabilities of probabilistic programs that they try to basically train on this data. And this paper, here's the title of the paper if you're interested, gives very interesting results showing that actually with probabilistic programs, while doing this learning, you can do quite some interesting stuff. Good. Now, let's go to the, let's say, probabilistic programs. And my slogan here is probabilistic programs are hard to grasp. So what I have here is a very simple program, and think about this as a one-dimensional line. We look at the positions, which are the positions at the natural numbers. So here's 0, 1, 2, 3, 4, etc. We start at some position. In this example, you start at position 1. And as long as x is strictly positive, you flip a fair coin. This is what this half means. And with probability half, you either go 2 positions to the right, or you go 1 position to the left. So what's it you see here? You are at some position, let's say position 2. With probability a half, you go 1 position to the left, and with probability a half, you go 2 positions to the right. The program terminates if you reach 0 here. And the question is, does this program terminate with probability 1? And we call this almost sure termination. And if this program does not almost surely terminate, then we would like to know what is the probability to diverge. So here, intuitively speaking, you could say the drift to the right is larger than the drift to the left, because in every position you go 2 positions to the right, or only 1 position to the left. So you basically drift away from 0. Yeah. So maybe this program is not almost surely terminating, but then you would like to know what is then the probability that this program will terminate. Good. The next example is an example that I took from this paper by Flyolet. It's not even using unbounded loops, because the previous example had an unbounded loop. So you may think, well, that's maybe a kind of a problematic case. So let's look at this example. You first draw from a geometric distribution with some parameter a quarter, x. You do the same for y. You add them up. You add 1 to it with a certain probability, or you don't add anything. So far, nothing special. And then you set r to 1. And now you have a for loop, so you're going to do 3 times some experiment. And what are we going to do is the following. Here we're going to take 2t samples from a Bernoulli distribution. So in terms of real code, this means that you start with 0, and you basically take 2t samples, and in every sample you flip a fair coin. You add 1 to this, basically this sum, or you don't add 1, and that's the skip statement. Okay, so that's happening in this IID statement over there. And then you check if s is different from t. I mean, t is the number that you sampled here, and you just want to know if s is different from t, then r becomes 0. Okay, so what you would like to maybe know is, okay, here you set r to 1, you do 3 times this experiment, so 3 times you do this thing, and every experiment you check, is s different from t, or is it the same? And if in all 3 of those experiments x is equal to t, right, then at the end of the day r will be 1. So what you're interested in is here is what is the probability that r equals 1 on termination. Yeah. And what this program has in common with the program before, it fits on a slide, it looks naively quite simple, but if you would like to answer those kind of questions, it turns out that this is much harder than you think. It's not easy to see. Good. The last of the one but last example that I have to motivate you why we're going to look at verification is a data structure. It's a data structure, it's called the insert, delete, find any data structure. So what's the idea? We want to build a dictionary, and this dictionary is storing numbers. And this dictionary is supposed to have 3 basic operations. Delete x means that you're going to get a pointer that points to x, and it removes the element x from the dictionary. Precondition perhaps that this x is indeed in the dictionary. Then you can add an element to a dictionary, so that adds a new element. And now it comes, there is a special method called find any. So what is this find any going to do? It's going to return an arbitrary element in the dictionary. We call this any, but together with the rank of this element. What's the rank of this element? It's 1 plus the number of elements in the dictionary which are smaller than the element you're picking. So in some sense you need to keep track. Okay, here I have my any element. How many elements in the whole dictionary are smaller than the any element? So you can imagine if I insert a new element, I basically have to check, is that element smaller than the any, because then the rank of the any is basically changing, right? Because I'm adding a new element to the dictionary which is smaller. Good, and we call this the rank. Good. Can we design such a dictionary such that all operations can be done in constant time? In constant time, I have to be a bit more precise, and I will be more precise on the next slide. So what Brodel actually showed in a paper 1996, he gave a randomized solution using a doubly linked list. So he said, okay, implement the dictionary by means of a doubly linked list, and for the rest, what you want to do is the 2 operations. One is on the left, which is delete. One is on the right, which means insert. You're going to make them randomized procedure. Now I don't want to go through all the details, but here you see the remove elements. So here this is the delete procedure. You remove an element x. Now if the remaining list has length 0, you basically have to set any to 0 and the rank to 0. Otherwise, if you just remove the any element, then you have to pick a new element, and you are going to do this by sampling, which means basically if there are n elements left in the list, you pick every element with probability 1 over n. So every element is equally likely to be selected as a new any. And of course I have to compute the rank, because then from the new element I need to know how many elements are smaller than that element. If that's not the case, it means if you did not remove the any element, then you're going to pick basically the value of the x element that you deleted. You take the value of the any element, and if the value of x is smaller than the any element, you decrease the rank by 1. Yeah, because you deleted an element which was smaller than the any element. And here is -1 because you cannot go, let's say, lower than 0. And then you delete really the data. And here is the insert statement. I don't want to go to all the details, but what is important is this statement over here. Here you see again a probabilistic choice. And you see with probability 1 divided by the length plus 1. So this probability depends on the length of your dictionary. So the longer this dictionary gets, the more elements it has, the lower probability it will have basically to take this element, to take the first, let's say, branch. And the higher the probability will be to take the second branch. Okay, so this is a very tricky kind of data structure, doubly linked list, plus this randomization, and even this randomization where the probability is not a constant, but it depends on the size of the dictionary, the number of elements which are in the dictionary. And what Brodal proved is that this is a data structure that implements the three operations with amortized complexity, which is an expected constant time. And he proved in this paper that there does not exist a deterministic implementation which has the amortized complexity which is constant. Amortized means that every now and then you do a constant operation or you do an expensive operation, and this basically the cost of this expensive operation is basically faded out because it's followed by many, let's say, cheap operations. Good, and this is what you would like to do is now you would like to be able to analyze these kind of algorithms, and you would like to be able to prove that, for instance, for this implementation, indeed, the expected runtime of all these things is constant. The amortized expected runtime is constant. Good. The last example, before I get into how to prove these kind of properties, is here is a loop. It basically, you initialize x to 1, and Boolean C is basically controlling the termination of the loop. So as long as C holds, we're going to execute the loop. And in every loop iteration, we're going to flip a fair coin. And based on the outcome, we're either going to terminate the loop because C is set to false, or we're going to take another loop iteration because C is set to true. And for the rest, what we're doing, we have a counter x, which initially is 1. And in every iteration, it's doubled. Now, this program, the question you could answer is basically, is the expected time until termination of this program finite? And it's not so difficult to see that this indeed is the case. Why? Because with probability half, in every iteration, you decide whether to terminate or not. And this is basically a geometric distribution. And you know that the expected value of a geometric distribution is actually, in this case, with parameter half, it's 2. So it's finite. So this will indeed have a finite expected termination time. Now let's look at the program on the right. This is very simple, right? It's just a countdown program. You just count down x, and this definitely has a finite termination time. There cannot be any argument about this. And now we put those two programs in sequence. So now we take the program on the left, followed by the program on the right. And the question is, does this program have an expected runtime which is finite or not? And the surprising thing is that actually on the left, this first program is finite, the other program is finite, but if we put them in sequence, this program actually has an infinite runtime. Now what's the intuition? How can you see this? The intuition is in the program on the left, you see that x is doubled in every iteration, right? So what do you get? What's the expected value of x on termination of the left program? It's something like a sum over the number of iterations. The probability that you take the next operation, the next loop iteration is 1 divided by 2 over I. And what's the value of x in that loop iteration? It's 2 to the power I, because you basically doubled x in every iteration. And this is pretty much infinity. Yeah? So that means that the expected value of x after the first loop on the left is infinity. And then you count down. Yeah, and therefore the expected runtime of the sequence of these two programs is infinite. Good. These are surprising effects that occur because of this randomization. And now what you would like to do is you would like to be able to prove these kind of phenomena. Okay? So you would like to provide hard guarantees. And by means of hard guarantees, I mean we're not going to simulate these programs and then try to see what every now and then happens. We really would like to have, let's say, proofs. Can we do things like model checking? Unfortunately not, because those programs are infinite state. Yeah, typically. So this doesn't work. Good, so what's the objective? The objective is to provide a powerful, I mean, we want to basically treat the examples I showed you, a kind of proof calculus, and we're going to use weakest preconditions to reason about these kind of probabilistic programs. And we don't want to do that by looking at the semantical model. I mean, for many of the examples, for instance, the random walk example I showed you, it's an infinite state Markov chain. Of course, you could start reasoning operationally about the infinite state Markov chain, but that's not what we want. We want to reason at the syntax level of the program, and that's very important. So, what I call no descent in quotes into the underlying probabilistic model. And we would like to push automation as much as we can. And I will get to this at the end of the talk. But that's a bit of a challenge. Because probabilistic programs are typically, in quotes, more undecidable than deterministic programs. So here is the arithmetic hierarchy of, let's say, to classify basically undecidable problems. So the decidable problems are basically here. Yeah? And everything which is on top of it, it's undecidable. And intuitively speaking, the higher you are in the hierarchy, so here you see you're at level 1, there you're at 2, at 3, at 4, and so on. The higher you are in the hierarchy, the more undecidable is your problem. Okay? So let's look at some elementary, let's say, decision problems on probabilistic programs. And the first issue that I have is I want to give you a probabilistic program, and I give you one input. And I want to know for this specific input, does my program terminate with probability 1? This problem turns out to be as difficult as proving the universal halting problem. That means for a non-probabilistic program, you ask, does it terminate for all possible inputs? So one input versus all inputs. And this means that this program, this AST program here, is as hard as the universal halting problem. Good. This turns out to be equally hard as computing the expected value. So remember, my example was something like, what's the probability that r equals 1 on termination? Or what's the expected value of x? Or what's the expected value of the sum of two program variables like x plus y? This is all, I mean, equally hard. So that's also as hard as solving the universal halting problem. And now, if you would like to determine whether a program can terminate infinitely many steps on expectation, then this turns out to be even more undecidable. So then it means that we are considering over here, here's the universal halting problem, Turing. Now I want to know, for all possible inputs, does a probabilistic program terminate on average infinitely many steps? This turns out to be one level more undecidable. Yeah. So this means that if we want to tackle these kind of problems, right, and would like to push automation, of course we have to do compromises there. No mercy. Yeah. Good. So what's the roadmap? I'm going to talk first about weakest preconditions and probabilistic extensions of it. Then I want to talk briefly about proof rules for probabilistic programs with loops. And then part 3, I would like to talk about relative completeness and automation. Good. So we're going back to good old Dijkstra. 1976, he wrote this seminal work on a discipline of programming. And this is all about weakest preconditions. I'm not doing this because I don't think you don't know this. I'm just doing this in order to fix the notation, but also to, let's say, contrast this to the probabilistic setting. So what are program states? Program states are just functions that map program variables to numbers, and here I take the non-negative rational numbers. Then we have predicates. What are predicates? They're just mapping from states to booleans, 0, 1. So they're just functions that map states to 0, 1. And then I can have a complete lattice because I can take the set of predicates and I can take an order, and my order is basically saying f is below g, so my predicate f is below g if and only if f implies g. Yeah, so if the set of states satisfying f is a subset of the set of states satisfying g. And then we can provide functions on predicates. That is called a predicate transformer. yeah, that takes a predicate and gives you a predicate. Good. If this function is, for instance, monotonic on this complete lattice, then we know by cleanest fixed point theorem that least fixed points and greatest fixed points exist, and we even know how to approximate them from below or from above. Good. Now, Dijkstra defined a specific predicate transformer. So we just consider WP, which is just a predicate transformer, and he called this the weakest precondition. So G is the weakest precondition, right, of a program P with respect to postcondition F, if the following two things hold. If P starts in a state satisfying G, it will terminate in a state that satisfies F. Okay, that's good. And otherwise, a P either terminates, so otherwise means if you don't start in a state satisfying G, so if you start in a state that does not satisfy basically the precondition, it either terminates in a state that violates F, or your program diverges. Right, so in terms of a picture, it looks like this. On the left, you see the input states. On the right, you see the output states. And if you start in the good state, in the green area, and you have, let's say, a run of your program, you end up in a state satisfying F, which is on the right top in the red part. If you, however, start in a state that violates G, two things can happen. Either you end up and you terminate in a state that violates F, what you see over here, right? Or you diverge. Good. And we use them for total, basically, program correctness. Then it's important that weakest preconditions are all about backwards reasoning. And that's good to, let's say, as a mindset of this talk. So suppose I'm interested in a program that is of the form C1 followed by C2. So how are we going to do that? Well, we're going to look at the post condition, and suppose the post condition is F. Now, the first thing what I'm going to do is I'm going to consider, let's say, the weakest precondition of the second part of the program with respect to this post condition. So this is, again, a predicate. Yeah. And now I consider this as the post condition of C1, and then I push this basically back, and this gives me the WP of the first part with as argument the post condition of C1. Okay? And this backwards reasoning is basically, to my opinion, one of the key ingredients also for reasoning about probabilistic programs. Good. Now, because, let's say, Dijkstra, we have a very simple syntax of my programs, which occur here on the left. You can fit basically the inductive definition of this weakest precondition on a single slide. I'm not going through all the cases, but on the left you see a syntax of the program. On the right-hand side you see the WP of this program, with the post condition is F. Clearly, if the program doesn't do anything, then this is simply F. No? If you do an assignment, then what you do is you take the predicate and you substitute in the predicate, basically you replace all occurrences of X by E. What do we do with P followed by Q? Well, just what I explained to you. You first consider Q, compute there the precondition of this thing with respect to F, and that's the post condition then of P. What happens with an if-then-else statement? You validate the guard. If the guard is true, you consider the then branch, which means P with respect to your post condition. If the guard is violated, you take the else branch and you evaluate this with respect to the post condition. Good. And finally, we have loops, and here we get fixed points. So now we have this while loop, this possibly unbounded loop. And the way to read this is as follows. Now, if the guard is false, then of course we need to establish the post condition, right? And this you see with this disjoint here, this disjunct non-F, non-phi and F. If, however, the guard is true, which is this case, then we're going to execute the body, which is P, and we have a recursion variable, capital X, and we're going to consider the WP with respect to that recursion variable. And this semantics of the loop is this least fixed point. The set of predicates with this ordering was, let's say, a complete lattice, and now what we do is we basically consider the least fixed point with respect to this function on this recursion variable. So maybe we have to maybe look at this a bit more careful. So here again is the WP of the loop, and here is my least fixed point. Same as before, if the guard is false, then you establish the post condition. If the guard is true, you execute the body, and you have this recursion variable. Good. This function, which is underbraced over here, you can prove that this is Scott continuous on your complete lattice. Scott continuous means monotonic, and you basically can intertwine basically taking suprema and basically suprema and the ordering. So that's nice, because now what it means is that you can apply cleanest fixed point theorem, and that means you can approximate the least fixed point from below by simply taking this function. You start with simply the predicate, which is the smallest predicate in our domain, which is false, and now you apply recursively again and again basically this function. So intuitively speaking, phi of f of n of false denotes the WP of running the loop exactly n times when you're considering the post condition f, and you start right from the initial state, which is the empty set. Good. There is a small twist that also Dijkstra considered already in his book, which are called liberal preconditions. What's the difference? The difference is the interpretation of a loop. Here you see that the while loop is now defined as a greatest fixed point, and that's the essential difference between a WP and a WLP. How can I try to make this a bit more explicit? Basically, the WLP of a program, right, that's used as partial correctness. The WP, as I mentioned before, as total correctness. So you have the weakest liberal precondition of a program with respect to f is either the weakest precondition or the fact that the program diverges. One, does it diverge? Well, the WP of P true tells you something about what's the, let's say, the weakest precondition under which the program is going to terminate. So if I'm going to take the negation of it, it's going to be the precondition under which the program is going to diverge. Yeah? So that means basically if the program is terminating on all inputs, so if it satisfies the universal halting problem, right, then the WLP and the WP are the same. Only for programs that, let's say, do not always terminate, there is this distinction. Good. Now the question is, what if programs roll dice? By the way, if there are any questions, please don't hesitate to interrupt me. Raise your voice in particular, because I can't see so much because of all the lights, but if there are any questions, just mention this. So the question is, if we have this framework of Dijkstra, what happens if you, let's say, allow, let's say, basically rolling a die? And that's all about verifying probabilistic programs. So here we go to what is called weakest pre-expectations, and this goes back to seminal work by Dexter Cozen, Annabelle McIver, and Carol Morgan. Good. So the idea is that we go from predicates to quantities. And to set the scene here, we have a simple example. So the program here that I'm considering is basically incrementing x by 5 with probability 0.8, and otherwise assigning 10 to x. And suppose I'm interested in the expected value of my program variable x. Right? Okay, then I hope it's not so difficult to see. What can happen is, well, with probability 1/5, we simply get the value 10. So this is the second part over here. And with probability in 0.8, we increment x by 5. So this x over here is the initial value of x. So what I get is I get this function. And this function says the expected value of x on termination is 4 times the value of x initially divided by 5 plus 6. Okay? Good. Let's try to do the same with the same program. So again, I'm considering this program. But now we're going to consider the probability that x equals 10. Good. Same program, different, let's say, post condition. So the question is, what is this probability? Again, there are two cases. The very simple case is, okay, when we set x to 10, that happens with 20%, so that's over here. With probability 1/5, the probability that x equals 10 on termination is 1. With probability 4/5, I'm going to take x plus 5. This is again the initial value of x. and I'm going to check whether the initial value of x plus 5 equals 10. Yeah? And if I can simply simplify this, so I get this as a function, and this simply says 4 times, if x equals 5, it's 1, so that's what the square brackets mean, right? I mean, I should have explained this, right? X equals 5, this is basically 1. If x equals 5, it's just a characteristic function, right? And otherwise, if otherwise. Yeah. So it's clear if x equals 5 initially, then no matter which branch you take, the outcome of the program will be 10. And if you substitute this, indeed you get 5 divided by 5, and indeed the probability then is 1. Good. Now keep this in mind, and now we get to weakest pre-expectations. So what is important in this example, the probability is always the probability on termination of the program. Okay? Good. So now we get to expectations. Read them as random variables. So expectations are functions that take states. States were just mappings from variables to non-negative rational numbers. But rather than mapping them to the Booleans, we map them to the non-negative reals plus infinity. ID, we want to talk about expected values of random variables. The expected value can also be infinite. And we restrict them to be here non-negative. Then we can define a complete lattice. We basically say, okay, we have to have an ordering on those functions. F, this function f is below g, if and only if pointwise they are below each other. Right? So this is the natural order on the real, on the non-negative reals plus extended on infinity. And now you can define functions, and those functions are called expectation transformers that take an expectation and map them to an expectation. So bottom line of this slide is basically an expectation, a random variable, is the quantitative analog of what Dijkstra called a predicate. Yeah. Good. So now we get to weakest pre-expectations. So now we have a probabilistic program, and we have this WP, which is again a kind of special expectation transformer. So it takes a post condition and it will give you a precondition. Yeah? But remember, they're not predicates anymore, there are those expectations, the functions that I showed you by means of an example. So this is how I would quote it in natural language. This function is the weakest precondition of this program with respect to that post condition if the expected value of this function after executing P on input S equals G of S. Again, I stress the after, as we have seen in the example, right? We always reason about afterwards, what happens on termination. So, examples. Same example as before. The weakest pre-expectation of this program with respect to x, what is the expected value of x after executing this program, is exactly the function we have seen before, this 4x divided by 5 plus 6. If I now change my post condition, and I ask what's the probability that x equals 10, that's again with those square Iverson brackets, that is a characteristic function that is 1 if x equals 10 and 0 otherwise. This turns out to be exactly the function we have showed you before. Good. So if you have a predicate, so f, capital F is a predicate, if I cast this as an expectation, I have to always put them, embrace them in those square brackets. Then you can think about such a statement as being the probability of this predicate, f, on the termination of the program. Okay? So in particular, it also means that if you have this, the WP of P of true, right? This is simply the constant function which is 1. This is the probability that P terminates. Yeah?
Joost-Pieter?
Yeah.
Just to be sure that I understand this right, so you're using the same formalism to model the expected value or statements about the expected value or the probability of some Boolean expected
Yeah.
value.
Yeah. Yeah. Because I want to make clear that it's not only expected values, you can also talk about expected values of arbitrary functions, but you can also talk about probabilities of things. There's not a difference there. So
expected value of an indicator is its probability.
It's the same. Yeah? Good. Maybe for the intuition, what I personally like quite a lot is Cosen's duality theorem. That is going to equate, let's say, forward reasoning and backwards reasoning. Backwards reasoning is the WP reasoning. And forwards reasoning I'm going to explain you in a minute. So what this is going to say is the following. Let's suppose that we're going to take the distribution over the final states. I mean, we're talking about a probabilistic program. So that means that a terminal state occurs with a certain probability. Okay, so in the end what we have is a distribution over all those terminal states. That's indicated by this mu p, and because this distribution may depend on the initial state, I have this s over there. Okay, now you run p on the initial state. And now you consider the post-expectation f, and what we're interested in here is the wp of p with respect to f, and remember that's a function that maps states to non-negative real numbers. Yeah? So this is why I there also have this s, and this is, if you look at it forward, it's nothing else than the sum over all terminal states of the probability that your program, when starting in S, ends up in T, times the value of F in that state. And here you see this looks, this smells, this, I mean, stings like an expected value. Yeah? And this is the way you should think about it. So you start in some state S, the program runs, it makes probabilistic branches all over the place. You terminate in some states. Here I have T1, T2, T3, T4, T5. You evaluate your post-expectation in all these states, and then you take the expected value over them. That's what happens on the left-hand side. And you can prove that this is the same as doing the WP. Good. So examples. These are the two examples I mentioned in the beginning. On the left, the random walk that moves 2 positions to the right or 1 position to the left. And this was this, a bit of kind of tricky example where you do this sampling. So here I'm interested in whether this program almost surely terminates. That means I'm going to consider the post-expectation, which is just a constant function 1. And then the WP of this program turns out to be the square root of 5 minus 1 divided by 2. And that's the probability that this program is terminating. So very interesting. You see that this program, I mean, only has rational numbers, but the termination probability is irrational. And these are the kind of phenomena that occur more often in probabilistic programs. If you look at the program on the right, here the question was, what is the probability that program variable r equals 1 on termination? And remember, I put this in those square brackets. And it turns out to be that the biggest pre-expectation is 1 over pi. Yeah. So you don't have to blame yourself if you could not answer the question at the beginning. It's simply not an easy exercise, right? Although the program looks, I mean, there are just 8 lines, right? Or maybe 9, but that's it. Yeah. Good. Like Dijkstra, you can define this by induction. So again, you have here the syntax of your program. On the right-hand side, you define the WP. For skip, again, the WP of a post condition f is simply f. If you do an assignment, you take the function f, and you just literally replace every x in that function by the expression e. Sequential composition is, as before, backwards. I'm going to skip this for a moment. I will make the slides available so you can read them offline. I will get to the probabilistic choice in a minute. So here is the if then else. If phi holds, and now I have to put that in square brackets, then I'm considering the WP. Now in the logical case here, there would be a conjunction. Now this becomes a scalar multiplication. And this was a disjunction, and this becomes now a plus. Okay? But for the rest, the reasoning is the same. And if you grasp this, then the probabilistic choice is also not so complicated. Because I have this choice, it means that with probability P, I have to consider the WP of the left-hand side with respect to my post. And otherwise, with 1 minus P, I have to consider the WP of the right-hand side with respect to my post. And you see the similarity with the if-then-else and this thing. And this is not so strange, right? Because this is nothing else than if flip P, then you execute program P, and otherwise you execute Q. Yeah. So that they are very similar is not so much of a surprise. What do we get for loops? We get a least fixed point. In a very similar way as dijkstra gets, you get a leaves fixed point. But that's the way it is. So let's look at this example again. The two examples I had before. This program over here. And I'm interested in the weakest pre-expectation of variable x. Good. So now I just apply the definition. Yeah, so I really switch off my thinking. I'm just doing the definition. So that means I look at the probabilistic choice, which was a weighted choice, 4/5 times the weakest precondition of this thing. There should be x plus 5, by the way, plus 1/5 of x becomes 10. So here should be x becomes x plus 5. There was a typo. And here you get 4/5 times x plus 5, right? Because I just replaced this x in this equation. And now 1/5 times 10, and then exactly I get this function. Same for the probability that x equals 10. Similar recipe. You take 4/5 times the WP of the left branch with the post condition, 1/5 of the right branch with the post condition. You apply the definition. You just literally do the substitution, which means basically replace basically this x equals 10. So you get x plus 5 equals 10, right? So you take this predicate and you replace this x by x plus 5. That gives you x plus 5 equals 10. And similarly here, you replace this x by this 10, and that gives you 10 equals 10. This is of course true, so you get exactly the function we have seen before. Good. For straight line code, this is relatively easy. What happens for loops? Similar as in the dijkstra case, you have this WP thing, and you can prove that this function is again Scott continuous. Then between his fixed point theorem, you get an approximation from below, etc. Yeah. What do you get in the expectation phi n of 0? This is this approximant. Is basically the expected value over the final states if you have done n steps of your loops. So if you have done n unfoldings of your loop, to be precise. Good. And now you can analyze these kind of programs, perhaps, if you're lucky enough to compute this least fixed point and so on. And then you can maybe ask the question, what's the expected value of x on termination? Notice that in this program you don't initialize c, right? So you get something like a function that depends on c if you would like to solve this question. And it's something of the form, if c equals 1, then the expected value of x is, I guess, 1, and otherwise it's basically 0. There is a small twist with liberal preconditions, very similar as what Dijkstra did. In order to that, we have to restrict our functions, f, to be probabilities. So notice those f functions map states to non-negative real numbers, or infinity. I'm now going to bound them from above, because I want to talk about probabilities. And loops are again defined by a greatest fixed point. That's the same as in Dijkstra's case. And how can you relate the weakest liberal to the WP? The weakest liberal precondition of a program is the weakest precondition, namely if P is just terminating, or it diverges, but now I get the probability that P is diverging. WP of P1 is the probability that P is terminating. So 1 minus this thing is the probability that my program is diverging. And that was the same reason as I had the negation before in the Dijkstra case. Now I get the 1 minus. Yeah. And that means that if your program is almost surely terminating on all inputs, the WLP is the same as the WP. So they only differ if my program every now and then, with positive probability, diverges. Yeah. And that happened, for instance, in my example of this random walk. Good. I mentioned in the beginning that one essential ingredient in probabilistic programming nowadays is what they call conditioning. So let me give you a small example on how to work with this conditioning. So this is a loopy program. Again, as before, C controls the termination of the loop. So in every iteration we have a biased coin. With probability P, we're going to set C to false and we terminate, and otherwise we take another loop. Good. For the rest, the program counts, and that's simply this I variable. Okay, so if I just look at this program, and only at those 4 lines, my claim is that this program models a geometric distribution. Yeah, basically saying that the probability that if I equals n at the end of the day, it's something like p to the power 1 minus p to the power I minus 1, because every time I take a next look, times p, and that's the probability to terminate. But now I observe that I is an odd number. What does that mean? It means I have data. Apparently I have some experimental data or empirical evidence that tells me I is an odd number. So that means actually that the probability that I equals even at the end is 0. So what's the probability that my program actually will provide you with an odd number? Well, that's simply the probability that you get 2n plus 1 iterations. Yeah, because that means that I equals 2n plus 1, that's an odd number. And that means I have done this assignment 2n times and that assignment once. And that's exactly this summation. And this is just a geometric series, so you can solve it. It's 1 divided by 2 minus p. Now, what's the distribution that this program produces? Now, the probability that you get an even number is 0. That's not a surprise because of the observed statement. So what's the probability that I get an odd number? First and foremost, it's a geometric distribution. This is these first 2 terms. You get something of the form 2n plus 1. But now you normalize, and you normalize by 1 divided by this quotient. So this is the normalization factor, this 2 minus p. So what happens is that the probability mass of all the runs that end here and actually find out that I is not odd but even, all this probability mass is distributed over all possible outcomes of having an odd outcome. Okay, so maybe I can visualize this to make this clear. So this is a geometric distribution with some value, I think 0.65. Yeah, with 0.65 I get output 0, otherwise I get 1, 2, and this is this exponential decay that you're all familiar with. Now I condition. Okay? What do I get? The only things I get are the odd numbers. So either I can get output 1, so be aware this is 0, this is 1. So you should compare this pillar with this pillar over there. And I made it very clear, the blue part should be roughly the same as there, and mind this is 0.25, this is 0.25. And the red part is the probability mass that was added because of the normalization. Intuition is basically, if you want, this can no longer happen, 2 can no longer happen, 4 can no longer happen, 6, 8, all those bars are no longer occurring. You accumulate the total probability mass of everything that you crossed out, and you distribute it over the remaining outcomes. And this is what conditioning does. And this is actually something that is used in, let's say, almost all probabilistic programming languages. And now you can reason about this. So what's the probability of a feasible run? That's the WP of P1. That was the probability to terminate before, but now be careful, I have those observed statements. So this becomes 1 minus the probability that you violate an observation. And now I can take the weakest pre-expectation of an observation. Basically, I just check whether phi holds. And if phi holds, I take f, and otherwise I 0. So it's something like an assert statement. Something like an assert statement, because we still need to normalize. How do you normalize? You can normalize like this. You take the WP with P with respect to your post, and you divide by exactly this probability. Because that's the normalization constant. And this is what Norrie actually proposed when they defined this R2 language. There is a small issue, a fine point. They assumed that all programs always surely terminate. If you don't do that, you better divide by the WLP in order to take the possible divergence into account. But the idea is clear. Also, you can apply, and that's why what I want to convey here is that you can apply this WP reasoning to also reason about programs with observed statements. Good. I'm going to skip this. I now want to show you that you can also do reasoning about expected runtimes of programs. And that the question is, how long does your program take on average? This is not so new to also try to apply WP to runtimes, because there is this work by Hanne Ries Nielsen in the 1980s that actually use Hoare logics, not WP, but Hoare logics to determine the runtime of an ordinary program. So what's the expected runtime of a program? Right, if you on input S, it's the probability is basically I, which is the number of steps, times the probability that your program will terminate after so many steps. Okay? So what we're going to do is we're going to define a function, the ERT of P with respect to T, and that will be again a function mapping states to, let's say, non-negative real numbers plus infinity. The runtime can be infinite, right? As we have seen. So this is the expected runtime of my program when the program starts in state S, and T is the runtime that comes after P. So typically you're interested in the ERT of my program with respect to 0. Yeah, but because of the backwards reasoning, we need this, let's say, this continuation parameter T here. Good. There is this example of the coupon collector. What is this kind of example? It's the following problem. I give you a 6-sided die, okay? So this has 6-sided dice and then other cases. How many times do I have to throw this 6-sided die, on average, such that I have seen all possible outcomes at least once? So I want to see a 1, I want to see a 2, a 3, a 4, a 5, and a 6 at least once. So you roll the dice, and I'm keeping track of how many times you get this, and I want to see all of them. And now you can do this for a 6-sided die, you can do this with a 2-sided die, a coin. You can also do this with a 10-sided die, and so forth. So this is known as the coupon collector. And here you see the possible outcomes. So if I have a 6-sided die, the outcome is 15. So apparently I have to throw this die on average 15 times to get this output. You can code this up as a program. I skipped the details here, but believe me that the expected runtime of this program is in theta n log n. Okay, so it's n is the number, I mean it's the how many sides your die has. I told you the 6-sided die, but if you have more, then it's n. And now the question is, can you formally derive such results by just doing a syntax-directed program analysis? The answer is yes. Otherwise, I probably shouldn't stay here. But there are some hurdles, right? Programs may diverge despite having a finite expected runtime. This program, with probability half, it counts down, and with probability half, it doesn't do anything. This has a non-terminating behavior, namely in every iteration you take the skip, but the probability that you take this infinitely often is 0. Yeah? Still, you would like to talk about the expected runtime of this program, despite the fact that there are infinite runs. Second hurdle, here is my random walk. You can go one position to the left or one position to the right, with probability a half times a bit, E. If E is 0, then this is the, let's say, the fair one-dimensional random walk, and with probability 1 you get to x equals 0. And the expected runtime is infinite. This is standard, let's say, this is knowledge that we know from stochastic processes. But if E is larger than 0, that means if E is larger than 0, right, then this probability to do a subtraction is smaller than a half, and there is a larger probability to add 1 to x. So the drift is away from 0. Then this program is not terminating with probability 1 anymore. But if E is less than 0, then this becomes minus, and then this becomes larger. So it means the drift to the left is larger than the drift to the right, and this program is almost surely terminating. So you see those 3 cases already say that this property is very sensitive to the values in your program. Good. And before we have seen that finite expected times is not something that is compositional, it can be infinite. Good. I'm going to skip this counterexample because of time. What I would like to show you is basically a transformer that we defined a couple of years ago, which is called the ERT. And again, it's backwards reasoning. So we want to compute the expected runtime of P1 followed by P2, followed by nothing. That's a 0. We do this first for P2 and then we do the same for P1. Okay? So this is the way it should be. The ERT of my program with respect to the post runtime 0 with respect to S is the expected runtime of P on input S. Good. You can define this by induction. This is the same as the WP. There is one slight difference, namely, here we're going to add in every entry a 1. So let me try to convince you of one entry, for instance, the if then else query. We assume that evaluating the guard takes 1 time unit, and then what you do is you take the expected runtime if phi holds of the left branch, or if phi doesn't hold, you take the expected runtime of Q. The same for a loop. If you would like to know what is the expected runtime of the loop, you have to evaluate this guard. This takes you 1 time unit, and then either you go into the body if phi holds, or you terminate, but if that's the case, you have to cope with the expected runtime that comes after the loop, which is F. Looks very similar as the WP as before, and that's also great. It's very simple if you know and understand what MacIver and Morgan and Cozen did, right? And it's sound. Yeah. So this gives you indeed the expected runtime of a randomized algorithm. So now you can take the coupon collector, provided you analyze the loop correctly, which means you have to provide a loop invariant or compute these fixed points, which you typically don't do. Then you can actually compute, using this kind of calculus, the expected runtime of these kind of randomized algorithms. Good. In particular, you can prove this, use this transformer to prove that a program is positively almost surely terminating. Notice, remember, this was high in the hierarchy of, let's say, undecidability, right? In a compositional manner, although the property past itself is not compositional. Yeah, I had this example where we basically had P had a finite expected runtime, Q had a finite expected runtime, but the composition has not. How are we going to dealing with this? Well, we first analyze the ERT of this Q. This ERT of this Q, in my example, will be some kind of function depending on X. Yeah, this function will be used as the post runtime of P. And now, of course, the expected value of X plays a role, and that was exactly the point that the expected value was infinite. And therefore you get that the expected runtime of the whole program is going to be infinite.
Quick question.
Yeah.
So for loop invariance, you mentioned, is it difference between definitions in probabilistic program versus normal program?
Yeah, I come to this. Yeah. Good question. I get to this. Now. Proof rules. We want to prove properties about loops. Loops are characterized by those fixed points. Those fixed points are, of course, not computable in general. And second, you don't want to, let's say, by hand compute them. You would like to have automated means. How do you do that with usual program verification? Loop invariance. What does that mean in terms of a probabilistic program? You try to capture the loop, the behavior of a loop, basically by trying to get an upper bound of it and a lower bound. So you basically try to sandwich the value of a loop by two values, upper and lower. Of course, if they coincide, you have exactly the meaning of a loop. Yeah, but typically you would like to have, so what we have here typically are proof rules that either give you upper bounds of the behavior of the loop or it gives you lower bounds. Good. So let's start with the upper bound because that's the easiest one. Remember, the semantics of a loop was just the least fixed point. So what is interesting is this function. And I will use this phi of f as an abbreviation of this function. And suppose I want to prove an upper bound. So you suggest me an invariant. I call this invariant I. What is an invariant here? It's an expectation. It's not a predicate. It's a function mapping states to non-negative real numbers. And suppose I want to prove that this is an upper bound. So I want to show that the WP of my loop with respect to a post is indeed upper bounded from above by your invariant. And preferably I would like to have basically a premise which hopefully is easy to check. And this indeed is the case. Why? You only have to look at this function and see. I mean, this is just, suppose that this P, the body itself, is just doesn't have a loop, so this is just straight line code. So here I can just apply my WP rules one by one, yeah? And I can check whether applying this function on the invariant is basically bounded from above by I. And this theorem says, if this holds, then I know that I is also an upper bound. And this comes directly from fixed point theorem. It's also known as Park's lemma. That basically says, okay, if this is a least fixed point, if I know that this function, applying it once on I is below I, then the least fixed point of that function is also below I. Good. So this means in particular, small example, here I have a simple loop. I guess an invariant. Suppose this is my invariant. And now I want to prove that this is an upper invariant. What do I need to do? I only have to check this condition, and believe me, that's easy. It's 5 lines of basically writing it down. The question, of course, is where does this I come from? I hopefully have time to get to this too. Good. Lower bounds are more difficult. So here is a lower bound rule that says, okay, if I want to prove that I is a lower bound of my loop. Okay? Good. What you would expect is maybe if I is a lower bound on applying phi once on this thing, it's done. This is not true, unfortunately. So what you get is a kind of a theorem that says if you indeed can also show some side conditions, then indeed I is also a lower bound of the loop. Again, where I comes from, I mean, you guess some, or you suggest one. And the side conditions are the loop terminates in finite expected time, and this comes a bit harder, for any state satisfying the guard of the loop, yeah, the difference between the basically of the invariant, basically this says in every loop iteration, the value of this invariant is basically at most, let's say, changing by C. So basically it says intuitively in every iteration, I can bound the change of my invariant in every loop iteration. Yeah. And you can prove if those two conditions hold, and then this theorem holds. And now you can apply this to the same example, and it turns out that actually the upper bound that I had before is also a lower bound. So it turns out that actually this program fulfills condition 1, because it terminates in finite expected time, because the expected termination time is only depending on this geometric distribution that terms termination. And it satisfies also this condition. This is something you can check. I'm not going to do that right now, but that's not so difficult. And then you can prove that this is a lower invariant. The last proof rule, the last proof rule I want to show is basically you can also strengthen the guard. So here I have this while loop with phi, and now I take the same body, but I take a strengthening of phi prime implies phi, right? And then what you can show is basically that if I is a lower bound of your strengthened program with respect to some, let's say, small deviation of your post f, then this implies that your invariant, your I, is also a lower bound of your loop program. Yeah. And this is a very simple proof rule, because it says, okay, take the guard of your loop, strengthen it, analyze this strengthened thing, and then you can take a conclusion over possibly the unbounded loop. And this is also applicable to diverging loops. Remember, this was not the case on the previous rule, because there one of the conditions was that the runtime is a finite expected runtime. The tightness of the lower bound depends a bit, of course, on the strengthening. But if this, for instance, strengthened program has finitely many states, then I can analyze this finitely many state program, for instance, by means of model checking. So I have a small example to show you this, and this is the 3-dimensional symmetric random walk. Now, what you should know about random walks is that a symmetric 1-dimensional random walk always, with probability 1 at least, will go to the origin. A 2-dimensional walk with probability 1 goes to the origin. And the interesting phenomenon is, for a 3-dimensional random walk, this is no longer true. Good. So I want to analyze this 3-dimensional random walk. Yeah? Good. Here are some plots on how this 3-dimensional walk runs. Basically, you are in a 3-dimensional domain. You have a point, and with equal probability, you can go in all, let's say, 6 different directions that you have. Good. So there is a result by Polya, Polya says the termination probability of this three-dimensional random walk is this impressive formula. Yeah. This is this number. Yeah. Good. There's no way that we're going to compute this exactly, of course. But can we maybe obtain a tight lower bound? Yeah. So maybe let's try to do that. So here is my program for a three-dimensional random walk. We can go in 3 dimensions, x, y, z. And this plus means, with equal probability, I either go in the x dimension, one to the right or one to the left, in the y dimension and in the z dimension. Okay? Now I'm going to strengthen the guard. What's the idea of the strengthening of the guard? It basically means you take this point. So here is my point. Here's my point x, y, z. What I'm going to do is basically I'm going to build a cube basically around this point. I'm very bad in drawing, but this point is exactly in the center of this cube, right? I know this is not true in my drawing, but that's the idea. And basically you have the size in all directions the same. Let's call this size maybe m. So what does that mean in terms of my program? I strengthen the guard from this blue thing into this thing, where I basically say x is at most m, y is at most m, and z is at most m. Actually, I built a cube with dimension 2m, 2m, 2m. Yeah? My theorem says if you can find a lower bound here, this implies that it's also a lower bound for that. That's what the theorem says. This is finite state. So put it into a model checker. Okay, let's do that. There are model checkers around. So here you see the value of m. Here you see the probability. The dashed line is the constant by Polya. And you see that for, let's say, for instance, here, you see if you start in 0.100, that's also what Polya actually says, right? I mean, let's go back to Polya. The termination probability of the three-dimensional walk starting from any neighbor location of the origin. So it also is important where do you start. Okay? And that's what you see in this plot. If you start, let's say, in one of the origin, that's the blue curve, in some point you get to this constant. If you start in 2 dimensions off by 1, you don't get to this constant, but it's approximating a lower value. Good. I have 15 minutes left and plenty of things to say. I'm going to talk about basically, I want to talk about automation.
Oh, we can continue next year.
Yeah, we can continue next year, but let's not do that. I can make the slides available and then you can read much more. I want to talk really about automation because that I think is very important. And the first thing I want to show you is probabilistic termination. We have seen almost sure termination for one input is equally hard as the universal halting problem. To check whether a program is past positive almost sure terminating runs in a finite expected time is even more harder. Good. I want to present you the AMBER tool, which has been developed by Marcel Moosbrugger, and he's a PhD student at the TU Vienna. He has some, let's say, restrictions on the kind of loops. So he has a simple loop, which means not a nested loop. And the loop body is simply a sequence of random polynomial assignments. So he looks at polynomials on the right-hand side. He supports several martingale proof rules, amongst others by Sriram and CAF in St. Petersburg. But also some other rules about, for instance, past, ast. And of course, in order to prove that something is almost surely terminating, you can also do the opposite. You can try to prove that something is non-ast or non-past. You can do this by means of what is called repulsing supermartingales. Krishnendu Chatterjee developed some techniques there. This is all is implemented in this tool. And some mild relaxed versions thereof. He uses algebraic recurrence equations, approximations of polynomial expressions, and actually exact moment-based generation techniques. I mean, you can give a whole lecture about the underlying technology. It's a C finite recurrence equations and so on and so forth. I'm not going to do that. What is important is the following thing on my slide. This loop body P is a sequence of assignments, and every assignment at line I is a probabilistic choice of terms of this case. So you can refer to your previous value of your program variable, but then this term can only refer to variables that are occurring before this variable in the loop. And this very strict, I mean, looks like a strict syntactic restriction means that you can actually always find a kind of closed form solution of these kind of loops. Where do you get, remember in my proof rules you always have to get something like a lower bound and an upper bound. Where does Marcel Moosbrugger get his upper bounds from? He simply takes the guard of the loop, this guard, and he's assuming that this is a strict inequality between two polynomials over the program variables. Yeah. So he doesn't need to guess this. I mean, he just syntactically gets it from the program. Good. Here are some example programs. I don't think this is irrelevant. So these are the internals of the proof of the program. You put in a probabilistic program. The ones that I showed you, slightly different syntax. It automatically tries to basically choose which of the rules you would like to apply. So it implements several proof rules. Yeah. And it basically selects which proof rule to apply. And then it basically tries to rule out by rule and try to find asymptotic bounds on those, let's say, runtime of your program. And it does a lot with what is underneath is Mora. This is the algebraic engine that they use in Vienna to reason about this. This has been developed in the group of Laura Kovac. And as you probably know, she's an expert on doing these kind of algebraic, let's say, analysis of loops for ordinary programs. But this is for probabilistic programs. Good. Here you see some results. You try to prove past for a couple of benchmarks. Here you see listed the several benchmarks. The group with Marcel Moosbrugger is not the only one, so you see here several different kind of, let's say, techniques. But what is good is in this what this summary tells you, that of those benchmarks, the tool was able for 23 programs to show that they are passed. Notice it is an undecidable problem, so there are many cases that you cannot solve. But there are also, let's say, it beats the other tools, let's say, significantly. So if somebody asks me what is the state-of-the-art tool to prove termination of probabilistic programs, I would say, I mean, look at this tool, and this is, to my opinion, most state-of-the-art. A journal version is coming up, I think, soon. Next, to my opinion, crucial kind of work is where do those bounds come from? Where do those invariants, those lower bounds and upper bounds come from? Right? Marcel Moosbrugger looks at the guard of a loop, but in general, this is much harder. And this is a TACAS paper that my PhD student Kevin will present you on Thursday, and this was already a kind of warm-up of this. So what are we going to do? We're going to try to automatically synthesize inductive invariants of probabilistic programs. Upper bounds, lower bounds, but also for expected runtimes. Okay? So this is basically the idea. We fix a certain template. The template says something about the shape of these invariants. Could be polynomial. In our case, it's piecewise linear. I come to this. Then we have a template, and this goes to the synthesizer. So a template describes, in fact, infinitely many possible instantiations, possible invariants. We pick one. We discharge it to a verifier. If that turns out to verify, then we know it's an inductive invariant. If it's not, the verifier will provide us with a counterexample, and the counterexample will hopefully try to refine our, let's say, set of possible instantiations. Yeah? And if we have checked all of them, yeah, then maybe it's either unset or maybe we have to change the template. Yeah, maybe we have to refine the template because the template was too coarse. Good. This is what we do here. We have I don't go to the details because I'm lacking a bit of time. Here is a program. It's actually a finite state program. You can put it into a model checker, but this is a hard nut for a model checker. Turns out to be the case. It's a bounded retransmission protocol. I'm interested in what's the probability of failing to transmit, and I want to know is this probability at most 0.05. So in terms of my WP, is the WP of this program of the probability that fail equals 10. I mean, if fail equals 10, then it means that my whole thing fails. So that corresponds to the fact of the probability of failing. If that is bounded from above by 0.05. That's my question. The answer is yes. And the tool generates you an invariant. And the invariant looks like this, plus 7 more summons. I'm very happy that I don't have to generate this invariant by myself. But the tool does this for me. Yeah? And what does that mean now? It means that now I can indeed answer this question affirmatively, yeah, by means of an automated tool. The only input I have to do is this thing plus this template, and then it generates for me all the variables in my template and says, wow, that's my invariant. Good. So we synthesize inductive invariance, and more precisely, we look for a piecewise linear inductive invariant. What does that mean? I'm looking for something which, let's say this was my while loop. I'm assuming that I is an upper bound of my while loop, and I is a lower bound of G. So that means I is inductive for F and G. That's what it means. And that's why we call it inductive invariance. Good. What's the approach? We fix a template. This is a simplification of the template we're using. Again, these are those square brackets, those Iverson brackets. Those BI's are Boolean combinations of linear inequalities over the program variables. Those A's are basically linear expressions over the program variables such that a certain side condition holds. And what is important, those B's partition the state space. So for instance, here you see an example. This partition the state space between C is one possibility and C differs from 1 is another possibility.
That's actually a question.
Yeah.
So is this template like your inductive bias?
Sorry?
Is this template that you're giving, is that your inductive bias?
This is, so basically what I'm assuming that this, my invariant is an instantiation of this shape. So if this is an invariant that of a different shape, then I will not find it. But if there is an invariant of this shape, I will find it. Okay? Good. You can check entailments. That's important, right? Because you have to check these kind of things. I is below G, or this thing is below I. So the question is how to check those entailments. This is something you can do because if this is a piecewise linear thing and that's a piecewise linear thing, you have to check whether F is pointwise below G. You basically have to check this formula, and believe me, this is a formula in quantifier-free linear arithmetic, and this is decidable. And with this you can discharge to an SMT solver. Good. If the program is finite state, this procedure is sound and complete. But it's applicable also to lower bounds, and that means it's lower bounds of, for instance, expected runtimes, and it's also applicable to actually expected runtimes. It uses SMT under the hood. The synthesizer, so this thing uses quantifier-free linear real arithmetic, and this uses quantifier-free linear integer and real arithmetic. Integer because you also have to deal with the program variables, and the program variables are assumed to have integer values. Good. I'm not sure whether Kevin is happy by this. I'm going to already show basically your results. This is a comparison to a model checker called Storm. And this is Seagis Pro, and you see that Storm actually have mens out and times out of many cases. For instance, on this BRP example, where we will, in our tool, can provide results. This was a tool presented at CAF last year. They learn kind of invariance by means of machine learning, so by means of data. And what we see here is that, this means that these plots, every point on the diagonal means that both approaches are equally fast. This means 10 times, this means 100 times. So this approach is beating this. I'm also happy to say that we also, sometimes we also beat machine learning. And this is an example where this is the case. Good. I have 4 more minutes. The only thing that I would like to say are basically 2 things. I have another brilliant PhD student working on program equivalence using probabilistic generating functions. Of course, program equivalence is undecidable. Program equivalence in the probabilistic case means you have 2 programs and you want to know, is the distribution that those 2 programs describe over your program variables the same? This is hard, but he was able to find a syntactic fragment like this. And he can show that if the while loop terminates almost surely, and if that's the case, and the body of the loop is loop-free and your invariant is a loop-free program, so you compare basically an implementation, a while loop, to a specification which is a loop-free program, and you would like to know, are they doing the same thing? Is your high-level spec the same as your implementation? In this syntax, this turns out to be decidable. And the way to prove this is using probability generating functions. And because I worked a bit on model checking, I want to show you one thing about model checking. This model checking of recursive probabilistic programs. Recursive probabilistic programs are probabilistic push-down automata. I'm skipping many details, I know. You want to check pre- and post conditions on recursive procedures. Then it's known in the literature that LTL is not expressive enough. Yeah, because you have one call, you have a second call, the second call gets basically a return, and then the other return, you have to link the first call to the last return. This is a property which is context-free. It's not regular anymore. So LTL is not sufficient. There is a language developed by Allur, Madhusudan at ETAPS called Caret, LTL version with calls and returns. And the slogan of this slide is that this model checking on PPDA, this means you have recursive probabilistic programs with finitely many control states, and you have pre-post conditions on recursive probabilistic procedures. This is decidable. So I guess you know this result by Vardy and Volpaire, right? You have a Markov chain and LTL formula. You want to know is the probability at least P. This is P space complete. If you have a qualitative case, and it's in the quantitative case, it's X time. For push-down Markov chains, result by Etesami Yanakakis, it says you give me an LTL formula, but now your Markov chain is a push-down Markov chain. Of course, you know this is infinite state, but still this is decidable. It's X time complete. And it doesn't matter whether you look at the qualitative case or on the quantitative case. And what my PhD student Tobias was able to prove is the following. You give me a push-down automata, but now a Caret formula. Caret means pre- and post conditions. You want to know what is the probability that my recursive probabilistic program, given a certain precondition, satisfies a post condition. Is this at least P? Yes, this is decidable. Wow. And this is, in this complexity, is still a gap, right? But at least it's great that this is decidable. And this has been actually presented last year at ETAPS. I get to the end. Weakest preconditions nicely fit the analysis of probabilistic programs. Several extensions of Cozen's seminal work and McIver and Morgan's seminal work have been developed. I explained to you expected runtimes. There is also an extension with recursion. There is an extension with separation logic, because we wanted to deal with those doubly linked lists or balanced trees and so on. And there is an extension with semi-rings. There is an extension with amortized complexity. This has been work over the last 10, 12 years. So this has been very, very, let's say, worked. I have been equipped with a series of powerful proof rules, lower bounds, upper bounds, but also proof rules for almost sure termination. A result that I skipped, but if you're interested, look at the Popple 21 paper. We proved that a certain syntax is relatively complete, which means there is a syntax format such that for every precondition, of every post condition in that syntax, and for every probabilistic program, you can express the weakest precondition also in that syntax. And that's nice, and it's in particular essential for tool development. I think there are first promising results towards automated analysis. And I like to finish with an outlook. What we're currently trying to do in my group is actually to build, I'm a bit exaggerating, but a probabilistic version of Viper and Daphne, a proof checker for probabilistic programs. And this will be based on WP, it will be based on those proof rules, it will be based on invariant synthesis, it will be based on techniques like K-induction and so on. And this is what we're currently working on, and we're trying to build a verification infrastructure for probabilistic programs. Good. This brings me to the very last slide. I already started this in the beginning. I'm only a messenger here. The work that I presented is really due to these people, these fantastic people, which is great to participate and cooperate with them. Thank you.
Questions? It's hard to see here.
Yeah.
Yeah, so you presented some rules for having, generalization of rules for invariance for loops. But these rules seem a bit, I would say, a bit ad hoc.
Yeah.
Is there any completeness reason for that?
Yeah. No. No. So there is a very nice proof. I skipped this for instance, for almost short termination. It captures many, even very non-trivial examples, but we don't know. We cannot even find a syntactic fragment for which this thing is basically complete.
Is it incomplete?
Sorry?
Is it incomplete?
I think so.
But we don't have any more.
No, but I doubt this. I would doubt it that, I can't imagine that this is complete. Yeah.
Both of them or just one?
Good question, yeah. Yeah, but this is something which is a very good point. This is something that we don't know. So it would be great to have a syntactic fragment for which certain, let's say, proof rules are, for instance, complete. Yeah, very good point.
Maybe this is related to the question I had, which is if you have a relatively complete result, why do you point to different papers for different proof rules? Is this a phenomenon of this that there's always something slightly better and then there's slightly better and yet another better one? So how's that?
First, these proof rules were already, most of them developed before the relative completeness result was there. So the relative completeness result was from 2021. Most proof rules were before that, 2018, 2014, 2016. And now we have this, let's say, relative completeness result. It means that you can basically express all WPs in that syntax. But I don't see how this then immediately gives rise to completeness of specific proof rules, to be honest.
Thank you.
Any other questions in this area? I'm just trying to be practical.
So I appreciate the perspective on probabilistic programs as mathematical objects, but when this, earthquake localization program is run, it runs on a real machine in floating point numbers. And as far as I can see, not thinking about it very deeply, SMT solver almost doesn't care. You could use it as a floating point number arithmetic theory. Is there any problem with verifying actual probabilistic programs that run on computers?
So we abstract from many things, right? So we don't look at, let's say, the machine-specific kind of characteristics or, let's say, specific floating point kind of things. We really look at the program code as it is, and we try to really, let's say, prove certain things and give hard guarantees there. I'm not sure whether I'm really answering the question, but I think we're not really looking at programs running on a machine.
Yeah, sort of on the face of it, an invariant in floating point theory is still an invariant. The SMT solver should be able to prove it. Is there anything that breaks if we limit the set of numbers we operate to this narrower set?
You will get imprecisions, and I'm not excluding the fact that if you compute certain things with floating points, you get wrong answers. Yeah, could be. Yeah. But I think that's the same in, let's say, ordinary program verification, right? I mean, if you look at Viper, these kind of infrastructures, they also, in the end, discharge to SMT solvers, and they suffer from the same thing. Yeah. I don't think that there is a substantial difference here.
Probably the first question I have is, you mentioned that the observe semantics in the program has been implemented in programming languages. Can you tell me how? I mean, if it's implemented with rollbacks, it would definitely affect, say, expected runtime math, for example. Sure.
So the way I explained it to you was basically using rejection sampling, right? I mean, remember my example, I took samples, and at some point, at the end of the day, I check, is this an even I or is this an odd I? And if it's even, I basically start from fresh, and I take, let's say, another run. Until I'm happy, that means until I get a run for which the outcome is odd. That is typically rejection sampling. That's very inefficient, so that's normally not what you do. So what people typically do is they use MCMC, and they have all kind of dedicated procedures to deal with this kind of conditioning.
Okay. All right, thanks. So the second question would be, you mentioned an expected runtime transformer?
Yeah.
And you mentioned it was sound. Do you think is it complete, or?
What do you mean by?
As in, is it? Do you believe it's complete as well, or do you?
What do you mean exactly here with complete?
Can I use? I'm hoping. Can I use it to derive expected runtimes for any positively almost surely terminating program?
In principle, yes, but you have to find, of course, I mean, it's undecidable in general, right? But the calculus as such is a vehicle that in principle is able to do that.
Of course.
Yeah,
right.
But of course you have to find, like in the coupon collector, you have to find this invariant, loop invariant, and this may take you a week or 2 or 3, or you don't find it.
Of course, right.
Yeah, but in principle, the calculus is indeed, and by sound it means if you would use WP and you would just add a counter to your program, like a ghost variable, and you just count, that is unsound. In particular, if the program has a positive probability to diverge. And the ERT transformer is sound in that case. Yeah.
I would like just try to understand, to see if I understand correctly. In usual deductive verification, just giving a good invariant doesn't give me a proof of termination, right? I just see that invariant is preserved, and then I see that if I quit, I can prove the postcondition. But you seem to say that if I have a good sandwich, not precise invariant, but just a good sandwich, on my loop invariant in probabilistic programming, I can extract some good information about the termination of my program. Is that correct?
No, let's be more precise. I mean, so I used, let's say, a general rule for lower bounds and a general rule for upper bounds, right? There are specific proof rules for instance, things like almost sure termination. So there you want to prove that with probability 1, your program terminates. And they're typically of the form, a couple of constraints, sometimes not easy. You have to find, for instance, a kind of a stochastic ranking function with a couple of properties. And if you're able to prove that, then you can conclude that your program is, let's say, for instance, almost surely terminating. But of course, I mean, proving and finding such, for instance, such a stochastic ranking function is again something that, which is very hard, right? That's why we look into those kind of inductive synthesis kind of technique in order to get those kind of, let's say, ranking functions, or in this case, inductive invariance in an automated way.
I see. Thank you.
Question this area. Who knew that sharing sessions includes running around? Thanks for a great lecture. I do have a question.
Okay.
What have you done with concurrency?
The true answer is basically nothing.
So why did you want my picture before?
So there is. I have at the moment a PhD student. She's working actually on separation logic with probabilities for concurrent systems. But it's fair to say that this is difficult. I mean, this is, and I wouldn't say that we know exactly how to solve it. So this is far from being tackled, I would say. And I hope to have convinced you today that first and foremost, discrete probabilities are already interesting and complicated enough. And
you have convinced me that it's really complicated.
Also. Yeah. So it's somewhere on the agenda, but it could take a while before I can answer the question. Yeah.
Any more questions? And if there are, please nod at that end.
I don't think the mic. What about non-determinism?
Yeah, that's a great question. So that's basically the main difference between what Cozen did in the end of the 70s, right, and early 80s, and MacIver-Morgan. So MacIver-Morgan basically extended, I'm exaggerating a bit or simplifying things a bit, but basically took Cozen's thing and added non-determinism. Yeah. So some of the things are, let's say, also applicable to non-determinism. So a proof rule for AST, for instance, is also applicable to programs that have both non-determinism. You have to be a bit careful whether this is angelic or demonic kind of non-determinism. But this kind of non-determinism and probabilistic choices. Yeah. But other techniques, like for instance, the CGIS technique I presented you is not yet, let's say, applicable directly to things with non-determinism. But it's definitely on the agenda, and it's an important topic. Yeah, thanks for the question.
Okay, it's getting late unless somebody who's really desperate. And I'm really getting tired of running. So let's thank the speaker again.
Thanks.